The sixth part of this tutorial deals with medium access control and cross-layer design with a physical layer. The medium access control is really central to the design and throughput of any wireless systems because it controls the way the medium is accessed by the various competing entities. Dozens of contributions are available today on both the basic MAC as well as the cross-layer designed MAC as well as the distributed cooperative MAC. We will hence concentrate on the throughput of distributed physical layer optimized CSMA-CA based medium access controls, as well as on some design guidelines on the MAC for distributed cooperative systems. We found the following interesting but have no time to deal with: Larsen's selection diversity, including fading and capture effects, which can be read up in 91. Also John Shears et al. Medium access control, which is a design and a study of cooperative diversity slotted Aloha. Also Dianati et al., who provided an analytical analysis of node cooperative ARQ schemes, which can be read up in 93. MAC is really the center of gravity of a communication system. It decides on many issues such as the transmit power levels and therefore immediately has an impact on the error rates, on the interference behavior. It would also decide upon the frame lengths, which of course determines the throughput and also the interference behavior. It would have an influence on the scheduling timings. It therefore influences the delays as well as interference, and it can also serve as a kind of IP packet buffering because there might be a IP packet splitting, which of course has an influence on general quality of service parameters. Generally, there are two types of traffics going through the network. One is the control signaling type of traffic and the other is the actual data traffic. And you would also have two large families of medium access control, which are the contention-based, in this case CSMA-type medium access controls, and also the reservation-type medium access controls. And then we may have a hybrid between these two, but let us concentrate on these two. Now I've given this table here where I showed what type of traffic can be accommodated within which type of medium access control. Now it is clear that anything which is sporadic and non-regular, kind of bursty, should be accommodated by the CSMA type of medium access control. So therefore control signaling to set up the network will likely to be accommodated within the CSMA type of medium access control, as well as bursty data traffic with no way to predict when the next packet will arrive. Contrary, the reservation type of medium access control will be very useful for regularized data like UDP data streams, but it is not useful for control signaling unless it is a very regular signaling which is there to maintain the system. It is not a priori clear when one has to switch between the two different data types, bursty and regularized data. So therefore hybrid medium access controls might be a suitable way forward, particularly for networks which are very limited in energy, such as wireless sensor networks. Now let us move on to the CSMA type of physical and MAC layer optimization. I skipped the reservation type optimization within this tutorial, but you're welcome to read up my publications in that area or contact me via email. Now the aim when we started that work on the CSMA type of medium access control was to provide a general mathematical framework which is able to quantify throughput and delay for that type of data propagating through the network. And that shall happen independently of the node density, the node distribution, the traffic type, the transmission interference radii, the path loss shadowing and fading models in general, just to give us a performance characterization of CSMA type of protocols, four-way handshake, stop and wait RQ, and another big bunch of different protocols. And ideally, we aimed at synthesize various optimum medium access control parameters. Now, how did we proceed? If you look at the problem of bringing some data from a source to a destination, you could do that at a very high transmission level, meaning you reach your destination in a single hop, like in this case here. But what you do when you transmit, you block communication between all these nodes which are just adjacent here. So if that node wanted to communicate with this node here, it couldn't do that because that communication is blocked. On the other hand, if we use a smaller transmission power, we are able to transmit in smaller hops here. So 1 hop, 2 hop, 3 hop, and finally we reach the destination. Clearly, whilst this communication goes on here, these terminals here can communicate at the very same time, potentially increasing the throughput of the network. But we shall not forget that the relay traffic, which goes from stage to stage, is redundant traffic and does not count to the usefully propagated traffic in the network. It is therefore a priori not clear what is better, to have it in a single hop but block more communications in the vicinity, or have smaller hops, allow more communications, but then also generate more redundant traffic. What comes on top is the physical layer. Imagine my aim is to transmit 1000 bits over the wireless interface. Now if I use a low modulation index such as BPSK, I would have a packet which is 1000 symbols long. Now that is a very long packet, and therefore there's a very high probability of collision. On the other hand, it is very robust because BPSK is known to be a very robust modulation scheme, so it exhibits very low error rates. Contrary, if I used a high modulation index such as 64 QAM, I would have very short packets, therefore have a low probability of collision if another communication happened at the same time, but I would have a high error rate because 64 QAM is very susceptible to noise and to interference. So the question is, can we all that capture in an analytical way and trade one against the other? Meaning, can we trade the modulation radii? The transmission radii? Can we trade the modulation indices? The answer is yes. And with my colleague Athanasios Gelias, who is now at Imperial College, we managed to find a closed form expression for the useful network throughput for these type of CSMA-type medium access controls. Now CSMA stands for Carrier Sensing Multiple Access. It means before I transmit, I sense the carrier. So let us assume that I am this packet here, this error here, so a packet is arriving in my buffer at that moment here. I'm listening to the channel and I hear the channel is not occupied. I wait a random time d, which is determined by the persistency factor p. If p is 1, I would transmit immediately. If p is very low, I would take a while until I start transmitting. Once d, the random timer, has elapsed, I would start transmitting my packet, which in our analysis we assume to be of the normalized length 1, whereas the slot times have a length or duration of small a. Now in that particular moment, somebody else receives a packet. He listens to the channel and hears me transmitting and therefore defers his transmission. That happens until I finish my transmission, and therefore that other person hears that the channel now is not occupied, would again wait a random time d, would start then transmitting its own packet, etc., until everybody who received the packet to be transmitted is served, in which case we have an idle period, just after which again maybe somebody receives a packet to be transmitted and the whole process starts again. We therefore have in a delay period here, which is random. We have a transmission period which is deterministic, and we have a busy period which is something between random and deterministic, which is the sum of both. And we do have an idle period I here. Also, what is interesting to bear in mind is that each packet will be received at the destination with a certain probability, which is 1 minus the frame error probability Pf. How to calculate the useful average end-to-end network throughput? That is very simple. That is simply the average useful time U divided by the average busy time B plus the average idle time I plus the average cooperation time C divided by the average number of hops from source to destination, because I remind you that the traffic generated in the relays is redundant traffic and the useful average network throughput has to be normalized by that amount. And we multiply all that by the number of bits per packet. How to calculate these values? We can calculate I, the average idle period, to be that here, where A is, I remind you, the slot period, G is the traffic arrival probability, and MT is the number of terminals which are in the transmission radius. And therefore that is a summation, an infinite summation over these terms here, and a simple mathematical rearrangement gives us a neat ratio given by equation 63. We can equivalently derive a busy period B and also the other quantities which are given here, the average useful period U, and you're welcome to look into details going to Kleinrock's paper and to our further derivations of these quantities. And these equations seem to be quite large and quite heavy, but they contain everything we want. Let us look, for instance, at this equation here. We have P, the persistency that I access the channel, PF, the probability that my frame gets lost on the way. We have G to be the traffic arrival rate. We have MT, the average number of terminals in my transmission radius, etc., etc. So we have all values in here, and these infinite sums converge pretty fast, so they are quite useful in characterizing these type of systems. As for the average cooperation time C, we can easily calculate it as being the average useful transmission time U multiplied by the number of cooperative links per relaying stage and divided by the strength of the cooperative data pipe with respect to the relaying pipe. For instance, if I use wireless LAN at 10 megabits per second to realize a relay, and I use ultra-wideband at 100 megabits per second to achieve cooperation, alpha would be 10. We also assume that within the cooperative stage we have a reservation-based medium access control. If you are interested in looking to CSMA-based MACs for the cooperative stages, please consult reference 94. Subsequently, we will look into the performance of this type of network. And I remind you, just to give you an idea what kind of choices we have a transmitter here, we have a receptor here, and we have the choice either transmitting directly or in 2 hops or in 3 hops. And that will be quite useful to understand subsequent performance graphs. What I plot here and what I will plot in subsequent graphs is the network spectral throughput in bits per second per hertz, and that is the transmission range as an examples in meters. And we have plotted 2 families here. The dotted curves are for a high signal to noise ratio of 10 dB, and the solid curves are for a low signal to noise ratio of -10 dB, and per family we have the case of BPSK, which is the blue curve, QPSK, which is the black curve, and 16QAM, which is the red curve. We have assumed a path loss of -30 dB per decade in distance, a persistency of 3%, a traffic arrival of 0.5, we have a normalized slot duration of 0.01, and we have B bits 30 multiplied by log2m, where m is the modulation indice. We also don't assume any cooperation, so we just have 1 antenna per node. Let us concentrate on the case of very low signal-to-noise ratio. That means we are at -10 dB end-to-end signal-to-noise ratio. And as you can see, the maximum of this family is achieved at this point here. And that point here is achieved if I use the blue curve, which is the BPSK modulation scheme, and I use a transmission radius of 4 meters. What does it mean? That means in that particular scenario of low SNR and no cooperation in all these parameters, it is useful that the whole network uses BPSK modulation and that we choose very short hops to transmit of 4 meters equivalently. So we would have 5 hops to reach my destination, which is at 20 meters. If we increase now the signal to noise ratio going to 10 dB, things change immediately. Now the maximum is here. And that is achieved if we transmit using 16 QAM. That means we transmit frames which are much shorter because, of course, the performance is now determined by the collision and not by the frame error rate due to the errors on the physical layer, but rather due to the errors at the medium access control. So therefore it is better now to switch to shorter packets, minimizing these collisions at the medium access control, and we see that using 16 QAM and we use a transmission range of 5 meters, therefore reaching the destination in 4 hops would yield the optimum end-to-end spectral throughput. Let's now look into cooperation, and here we don't look exactly in the cooperative stage, but what we assume is an alpha going to infinity, meaning we neglect the time and efforts needed to facilitate cooperation. We just assume that we have 3 nodes which cooperate and therefore effectively emulate a 3x3 MIMO systems. The other parameters remain the same, but what we see is now that things changed. If we have cooperation, we see that the maximum will be here. That means we should use basically a 5 meter transmission range. We will reach the end, the destination, within 5 hops, and we should use QPSK in this case. If we go up again in signal to noise ratio, it turns out that 16 QAM is again a good choice because again the errors are determined by the medium access control and not by the physical layer. And the best way to transmit is now in very large transmission ranges, which is 10 meters. So therefore we would reach our destination basically in 2 hops. Meaning if we increase the number of cooperation, we will therefore increase the modulation indices which can be used and also increase the effective transmission range which can be facilitated. Let us now look at the cooperative pipe. So what we have done here is we did not assume alpha going to infinity, but we assumed, okay, let's say the first family of curves, which are the solid curves, alpha equates to 1. That means the relay pipe equals the cooperative pipe. Throughput is generally very low, as you can see. But in any case, because we have chosen a fairly high signal to noise ratio of 10 dBs, it turns out that having a transmission radius of 10 meters is optimum, meaning we will reach, no matter what happens in terms of the cooperative pipes, our destination in 2 hops. We always assume 3 nodes cooperating per stage, but what changes is the total throughput, and also the modulation indices has always to be 16 QAM. Now if we go down in the signal to noise ratio, meaning we go to 0 or minus 10 dB, of course these curves will change in a highly nonlinear fashion. So it is not a priori clear what is the optimum choice for these type of networks. Now in terms of the channel code, we pose the question, is it really useful to utilize a channel coder from a spectral throughput point of view? Because bear in mind, if you use a channel coder, you are effectively reducing the spectral efficiency because you add redundancy. We are talking now of a signal to noise ratio of minus 10 dB, so it is very low. We have no cooperation and 1 antenna per node. And again, we have the 2 families here. One family, the solid line, is without a channel code, and those dotted are with a channel code. Now, for very low signal to noise ratios, the maximum is here. Meaning, what we should do is, we should transmit with a transmission radius of 5 meters, meaning we reach our destination in 4 hops. And we should definitely use a channel code in conjunction with BPSK. That is clear because a channel is very bad. loads of errors occur at physical layer, so therefore BPSK is a robust modulation, and the encoder, the channel coder, will yield additional robustness. If I go up now in the signal to noise ratio, we go from minus 10 dB to plus 10 dB, we see that things change suddenly entirely. So my maximum suddenly is here. That means, again, we have to use 5 meters transmission range, but the optimum now is not with a channel code. The optimum is without a channel code and using 16 QAM, which means that most errors occur actually at medium access control. The physical layer can already not help so much with a robust modulation encoding scheme. So it is, from a spectral point of view, actually better not to use a coder because it yields a higher network spectral throughput. Now I'll finish now this part here on the medium access control design. The reservation type of physical layer medium access control can be found in my publications, but this type of physical layer medium access control for the CSMA type of protocols is very useful in building the general framework for these type of networks, which of course will in one way or another be used in ad hoc networks, in sensor networks, as long as there's a random component to the transmission choice. The next section will be on the future outlook of cooperative transmission.